The purple solution is aqueous potassium permanganate. The colorless solution contains iron 2 plus ions. When we combine them, a redox reaction occurs. The permanganate ion is reduced to manganese 2 plus, and the iron is oxidized to iron 3 plus ion.
An oxidation reduction reaction is another powerful type of reaction that we use around us all the time. Redox reaction, which is the abbreviation for it, redox reactions are used in batteries, and we all use batteries for cell phones and all kinds of things. It's also used, though, in our bodies, like getting oxygen from the outside to inside is actually a type of a redox reaction. So anyway, in a redox reaction, you have electrons that are transferred from one reactant, which is called the reducing agents, to another reactant, which is called the oxidizing agents. And it's important to know where electrons come from and where they go to in a reaction, all right? And they're very common, they're very powerful, there's lots and lots of uses for it, and let's talk a little bit more about what a redox reaction is. At this point, I need to introduce my friend Leo the lion, and Leo says, "Grrr!" All right, sound effects not necessary. Leo the lion says grr, and Leo says grr is an acronym that will help you. Leo stands for lose electrons oxidized. Grr stands for gain electrons reduced. So something that is oxidized has lost electrons. And you can see there that the zinc is losing 2 electrons to become zinc 2 plus. So notice that losing electrons means that electrons will be products. Grr is gain electrons reduced. So the copper 2 plus is gaining electrons to become copper metal. Reduced means electrons will be reactants. All right? So oxidized and reduced are real common. Unfortunately, in the real world, a lot of times people use reducing agent and oxidizing agent instead of oxidized and reduced. Now, something that's a reducing agent is something that's been oxidized. So zinc has been oxidized. Zinc is the reducing agent. And something that's been reduced, like copper 2 plus, is oftentimes referred to as an oxidizing agent. So copper 2 plus is the oxidizing agent. It's allowing the zinc to be oxidized. I guess that's the use for it, but chemists would call copper 2 plus being reduced. I'm just the messenger. I apologize for the confusion. I have nothing to say about it. Anyway, if you don't like my Leo the lion says grr, which is fine, you can use oil rig. Oil means oxidation is losing. Rig is reduction is gaining. Either way you want to do it is fine. But understand the terms oxidized and reduced, and know that the agents are the opposite. So reducing agent is something that's been oxidized. An oxidizing agent is something that's been reduced.
When a piece of copper metal is placed in a solution containing silver ions, solid silver crystallizes on the copper. While the silver crystals grow, copper ions are also released into solution, giving the solution a blue color.
This is a cool reaction. You can take a strip of copper metal and put it in some silver ions, and after a while you begin to see that kind of mossy stuff grow on the copper. Believe it or not, that mossy stuff is silver metal. It's kind of unpurified silver metal, but it is silver metal. And a blue color pops in. Blue is often the color that's associated with a copper 2 plus ion. So this is an example of a redox reaction. And if you have a redox reaction, something has oxidized and something is reduced at the same time. You can't have just one part being oxidized and one being reduced. They have to be done at the same time. Oxidized species become more positive. So copper going to copper 2 plus means that the copper metal, copper as a solid, has lost 2 electrons. It becomes copper 2 plus. So copper has been oxidized. It's lost electrons. Reduced species gain electrons. They become more negative. So notice that silver went from a positive 1 to silver 0, which is what Ag solid is. So it became more negative because it gained electrons. And what we're doing here by looking at more positive, more negative, we're really using oxidation numbers, and they can help by figuring out what's been oxidized and what's been reduced. Here's a reaction. Iron metal, which is Fe solid, reacts with copper 2 plus to make copper metal, Cus, plus iron 2 plus, Aq. And it says which of the following is correct. And we've got reduced, oxidized, blah, blah, blah. Okay, so first of all, notice that the last 2 answers are both reduced and or oxidized. And you have to have something oxidized and something reduced at the same time. You can't have 2 species reduced and 2 species oxidized. So C and D are out. Now, iron is going to iron positive 2. So iron on the left is losing 2 electrons. It's becoming more positive. We would say that iron is being oxidized. Copper 2 plus is becoming more negative as it goes to copper. So going from 2 plus to copper 0, which is what copper solid is, that's becoming more negative. It's going towards negative numbers. So copper 2 plus is gaining electrons. Copper 2 plus is being reduced. So answer B would be the best answer here. Here's the actual, what's called a half reaction that shows the electrons. Remember, electrons are always negative. So positive 2 for the iron and 2 negative 1 electrons. That whole thing goes to 0, and that's what the iron is. And you can do the same thing on the copper side too. So oxidation numbers can be helpful. Oxidation numbers usually are just equal to the charge that you'd experience on the ion, but there are some exceptions. So these are the official boring rules. If free elements are always 0 for the oxidation numbers. So if you have zinc solid, copper solid we saw in the last slide, O2 gas, bromine is a liquid, sodium metal, mercury is a liquid, helium gas, all going to be oxidation numbers of 0. And again, most of the time, the second one there, it says the most simple ions, the charge literally is the oxidation number. So chloride has a -1 charge. It'll have a -1 oxidation number. Magnesium 2 plus would be positive 2. Aluminum 3 plus would be positive 3, etc., etc. Now in compounds, polyatomic ions, stuff like that, fluoride, always -1, oxygen, usually -2, and hydrogen, usually +1. There are some exceptions for O and H, but usually that's the way it rolls. And the overall sum of the oxidation numbers is going to be 0 for a compound or equal the charge if it's an ion. And I'll show you some examples of how this works here in a little bit. So in this example in the upper right-hand corner, you have MnO2, manganese 4 oxide, reacting with aluminum to make manganese metal and 2 aluminum oxides. Well, the aluminum, which is by itself, and the manganese, those are both elemental versions, so they'll have oxidation numbers of 0. And on the MnO2 and the AlO2, you have oxygen, and oxygen is usually -2. So in MnO2, if oxygen's usually -2 and there's 2 of them, that's -4. And the manganese is going to have to balance out that -4 with its own +4 because MnO2 is neutral. So that's why the Mn is +4. And in aluminum oxide on the right, oxygen's usually -2 and there's 3 of them, so that's -6. The 2 aluminums have to balance it out. If each aluminum is +3, it'll balance it out, no problem. So that's a very fast way to look at oxidation numbers. It's mostly just about what the charges are in the species. For H2S, all right, if you wanted to figure out the oxidation numbers, well, hydrogen's usually +1, and there's 2 of them. So sulfur is the one that would be a little weird to figure out. So what you can do is that the overall molecule is neutral. So the overall molecule is not going to have a charge. And you know that there are 2 hydrogens, each at +1, and we just don't know what the one sulfur is. Let's call that X. So when you solve for this, 2 times 1 is 2, 2 plus 1x, or 2 plus x equals 0. Put the 2 on the other side, x comes out to be -2. So the sulfur here has an oxidation number of -2. And that kind of gels because sulfur is in group 6A. 6 minus 8, those are usually -2, and that's what we're seeing here for sulfur, so that doesn't seem too crazy. We can also do the same thing for sulfur in sulfite, all right? Now, sulfite is a polyatomic ion, but sulfur is going to have an oxidation number and all that. So what we do is we say that, well, oxygen's usually -2, like we said, and there's 3 of them, all right? So the 3 oxygens times the -2 charge plus whatever sulfur is, and there's 1 of them, so 1x. But while the last example, everything equaled 0, here everything equals -2 because this thing has a charge on it. So when you do the math for x, it's like -2 equals x minus 6. So you put the -6 on the other side, it becomes a +6. 6 minus 2, this sulfur is +4. So good old sulfite sulfur is +2, but notice that sulfur in the H2 S was -2. So you can have a variety of numbers, especially when you get to the central atom of polyatomic ions. But this terminology, this format, will allow you to figure it out no problem. You can then see what's happening.
The atoms in hydrogen fluoride have oxidation numbers of +1 and -1 respectively. These are the charges the atoms would have if the bond were completely ionic. The oxidation numbers on the atoms of the perchlorate ion indicate the charges they would have if the transfer of electrons were complete. Such complete transfer, however, does not occur in reality.
So H and F, H is +1, F is -1, and that's not a big deal because those are the charges you would normally expect for those compounds. But when you get to something like perchlorate, ClO4-, and you want to figure out the oxidation number, it's usually the central atom which is going to be unusual. So oxygen's -2, and there's 4 of them, -8, but -8 plus the chlorine equals -1. So when you figure out what the chlorine here is going to be +7. Now, this isn't an actual ionic charge, but it is what the chlorine would be if you'd rip the oxygens out. Oxygen's more electronegative than chlorine, so it is going to pull electrons more its way. But this is useful then to figure out if you have an oxidation-reduction reaction or not. If you know that chlorine's +7, you can see if it's changed to something else, and you'll be good to go. Single replacement reactions are a type of reaction where you have like a piece by itself and it's changing places with the corresponding piece in a second species. Now I know that's about as clear as mud, so let's look at an example down there where copper in the first one is reacting with silver nitrate. And copper and silver are both metals, they're both positive cations, so they're going to trade places. And you end up making then copper 2 nitrate, because copper usually is +2 more often than not, and silver metal. So that's an example of a single replacement reaction. The copper and the silver trade places, but there's no corresponding anion with the copper, so it's only in this case like the metal that trades places. The second example is similar. Magnesium and hydrogen are both positive, so they're going to be the parts that swap. So magnesium starts dancing with chlorine, and hydrogen is by itself. Now hydrogen's a diatomic, have no fear of ice clear brew, so write it as H2. But anyway, the important part here is that all single replacement reactions are redox reactions, all right? I don't know of any exceptions to this. So if you know about single replacement, it can make the world a little bit easier. You know automatically it's redox. Now to confirm that it's redox, you can look at the oxidation numbers. Now real briefly here, I'll tell you what the oxidation numbers are. The elements by themselves are 0. So copper, magnesium, both 0. The silver and the hydrogen gas are also both 0. But it's the other pieces that aren't 0. So silver and silver nitrate is +1. The nitrogen, +5. Oxygen, -2. Those are the oxidation numbers. You can pause the video and work these out to make sure I'm right, by the way. Copper, +2. Nitrogen, +5. Oxygen, -2. On the bottom, let's finish this off. Hydrogen's +1, chlorine's -1. Magnesium chloride, magnesium's +2, chlorine's -1. Now, why I did that? Notice how copper went from a 0 to a +2. Copper had to lose electrons to become +2. So your copper metal goes from 0 to +2. It's been oxidized. But if something's oxidized, you have to have something reduced. Well, notice that silver went from +1 to 0 on the other side. So the silver was gaining the electrons. It was being reduced to make silver metal. And you can do the same thing on the bottom. Magnesium is being oxidized. It's going to +2. And the hydrogen, H+ ion, is being reduced. It's going to H2. These are the value of oxidation numbers. You can tell by a change in oxidation number that something's been oxidized or reduced. Now notice in the first example, nitrate, nitrogen's +5, oxygen's -2, and that doesn't change on the other side. Nitrogen's still +5, oxygen's -2. So nitrogen and oxygen were not oxidized or reduced. There's no change in the oxidation number. And the same thing for chloride in the second example. It's -1 in HCl, it's -1 in MgCl2. Chloride was not oxidized or reduced in that reaction. So it can be pretty cool in telling what's been oxidized and reduced.
Nitrogen monoxide is a colorless gas, which we can observe when we bubble it through water. When it contacts air, and therefore oxygen, an oxidation-reduction reaction quickly converts it to nitrogen dioxide, a visible brown gas. When heated iron comes in contact with gaseous chlorine, a reaction immediately takes place, forming a dark brown solid, iron 3 chloride. This oxidation-reduction reaction involves a transfer of electrons from atoms of iron metal to atoms of chlorine, a halogen.
Redox reactions can be pretty spectacular, and both of these are examples of them. You can see they're for nonmetals and nonmetals, metals and nonmetals, all different kind of capabilities and reaction types will happen when it comes to redox. And there's oftentimes a lot of energy given off, and they're pretty cool. The important thing about redox, once again, is that when you hear reducing agent, that means that things are oxidized. And if you hear about oxidizing agents, those are things that are being reduced. And in the real world, if you listen to podcasts and health things, they'll say, oh, well, this is a great reducer, this is a great oxidizer. They're usually referring to reducing agents and oxidizing agents, but it's not all the time. So it can get really confusing. And I have literally stopped people in presentations and said, do you mean oxidizing agent or oxidized? And they have to think a little bit. But anyway, you should do this too if you get to it, because it can be very confusing. And all scientists face this. The joys of being a scientist.